So here we have a conformation of 1,2,4-trichlorocyclohexane. Now we're gonna give priority to each of our carbon stereocenters with our chlorines on here. So we know that for our first one, it has to be R. So we look at this carbon here, and this would be attached to a hydrogen, this is attached to a chlorine, and then we have our two carbons, so we have to look further down the line. So we know that this is gonna be 1, this is 4, and then this one is going to be 2 because it has this chlorine, which is a bigger group, so it has a higher atomic number compared to this one. So 1, 2, 3. So that would be counterclockwise, but since the hydrogen points out, we're going to actually flip it so that it becomes R. So that's good. So now we move to this one. So this is, of course, 1, and then we have 2 over here because of the chlorine, and then 3. So that's clockwise, but since the hydrogen points out, it's going to be S. And then we move to our fourth one, where we have chlorine again, and this other chlorine is going to give this carbon priority 2 because it's closer rather than this side. So 1, 2, 3, that's clockwise, but the hydrogen points out, so it becomes S, and that's our formation.
So here we have, again, the two different conformations of 1,2,4-trichlorocyclohexane. This first one here, due to the fact that it has 2 in axial positions, it is going to have more steric strain and therefore is going to be a higher energy conformation. This conformation we have here is less stable because it requires more energy to keep it in this conformation. Moving on to our second conformation, here we have 2 of the big groups in the equatorial position and only 1 in the axial. And due to the fact that they're in equatorial positions, they have less interaction with each other. And when observing these two, again, this is an equatorial and this is an axial, therefore there's less interaction, which is going to make this a more stable conformation of this molecule.
So here we have our 2 conformations. So now we have to figure out their relation to each other. So by looking here, just imagine there's a mirror. We have having a mirror image and also these 2 chlorine atoms. But then we come to these ones, the chlorine on the 4th carbon atom, and they are not mirrored in each other. So it's not an enantiomer. Now we look and see if they're identical. If we put this one on top, you can clearly see that they are not identical. Even if we move this all around, we have this one pointing out, this one's down, and that's out. Like, it just doesn't work. So we know that they are not identical, so they're going to be diastomers because they're not mirror images of each other, and they're also not superimposable on each other.
Alrighty, for the first conformation, we see here that this 1 chlorine is going to be in equatorial position. Chlorine on the position 2 is going to be in axial, and chlorine on the position 4 is also going to be axial. All of these are in cis conformations due to the fact that they all are pointing in the up direction. When we look at the second conformation, here we see that chlorine 1 is in the axial position, chlorine on carbon 2 is going to be in equatorial, and chlorine on carbon 4 is going to be in also equatorial position. And here again, we also have a cis conformation because we have all of these pointing in the up direction.
So here we have another conformation of our molecule, but we just flipped the absolute configuration. So let's just assign our priorities again. So we want 1s, 2r, 4r. So here we have our chlorine on position 1, so we assign a priority 1, and then this one would be priority 2 and 3. So we go, counterclockwise with the hydrogen pointing back. So this is S, which matches what we need. Then we go to the chlorine on the 2nd position. So we have a hydrogen out, and we go 1, 2, 3. That's clockwise to make R, that's right. And then we go to our chlorine on the 4th position, and we have a hydrogen pointing back again. So we go 1, 2, 3. That's clockwise, makes R, that's what we want. So now we're going to compare it to our lowest energy conformation from the beginning. So, as you can see, these are enantiomers because we have our chlorines in our axial positions both beside each other, and we have these chlorines pointing out, and we also have these chlorines pointing back. So they are mirror images of each other. But they are not superimposable as we place that on top. They just don't work.
So here we have the two conformations, which are enantiomers of each other, and here we're looking to see if they are meso compounds. So to determine meso, we have to find a plane of symmetry, but if there is no plane of symmetry, then we have no meso structure. So when we observe this first conformation, we see that when we split it down the middle here, we do not have equal sharing of the chlorines on each side. If we try and cut this and form a line here, we have the same problem of two being on the left, one being on the right. And this is true for any plane of symmetry that you try to put through here. There is going to be a split between left and right. On the second molecule, again, we have the same problem. If we make these planes of symmetry through any form, we're not going to find any form of plane of symmetry that has equal sharing of these chlorine atoms on each side of this molecule. Therefore, neither of these conformations are meso structures.